All right, so this week you only got me. We haven't got Bob or anyone else to talk, so you're going to hear me for the next, I don't know, at least hour and a half or so. Welcome. Obviously Bob had a bigger draw because this place was packed last month, right? And now look, I talk and there's a handful here, but the weather. Oh, okay, the weather. I'll blame the weather. Anyway, thanks for coming. I haven't really got much to say on the chapter, unless Bill or Ken's got anything. Oh, Ken's gonna.
Yeah, there are a few. I've got a list of the paid members. I'll pass it around. Some of you, as I was going through them this week, you haven't given us your national number. And one of the stipulations of being a local chapter is you have to be a member of the national organization. And most of you probably are. You just don't, you're like me, you don't carry the card around and you don't have the number memorized. So just next month, bring the number if your name's on here and it shows that you haven't given me a national number. You can pass those around. Martin, I need your national number.
Ha ha ha, got my card here. Look, I can give it to you right now. There you go.
Thank you, sir. Thank you. It's called service.
Yes, we try. Okay, with that then we'll just move on into the presentation. A little bit of background about me and why we're talking about flammability today. So I've been involved with aviation aircraft since I left high school. When I left high school, I moved down to, I was born in Bellingham, which is in the middle part of England. I moved down to a place called Hatfield, which is just north of London. And I did an apprenticeship with, at the time it was Hawker Siddeley, but it was the original de Havilland factory where the Comet, both the Comet Racer and the Comet passenger aircraft was designed, the Mosquito was designed there, the Tiger Moth was designed there. All of the old de Havilland, it was the original factory in Hatfield. A lot of history there, great museum with the de Havilland aircraft. So I was fortunate to be part of that apprenticeship scheme. Also got a degree in aero engineering at the local Hatfield University. I went on, did 2 years following my finishing of the apprenticeship, working in design. I love drawing, designing, and so I became an interior designer, worked in the interior furnishings drawing office with big boards and drawing with ink, and I mean I love it, the old days, old school. And I wanted to move on and get more experience, and so I actually left and moved down to work for Bristow Helicopters in Red Hill, which is Surrey, south of London. Red Hill is the home of the Tiger Club, which some of you, I don't know if you've heard of that, but they famous flying club in England. Spent a year there, decided I had enough of helicopters. Sorry, Dave.
Remember, it's the most fun you can have with your clothes on.
I wish I'd known that then. Anyway, so I left there, and then I joined Britannia Airways at Luton Airport, which is once again just north of London again, and became their engineering manager after working through the ranks there. Britannia were the first airline at least in England, that had Boeing aircraft, Boeing 737s. And so I got indoctrinated into the Boeing system, having learnt the British system with de Havilland and Hawker Siddeley. Now I'm working with American materials, American fasteners. And Britannia also were the first operator of the 767 when that came out back in the early 80s. And so I got sent over to Seattle to do some training and fell in love with Seattle and decided to move on. So that's why I got over here. I worked for a company, Heath Techner, who were at that time based in Kent. They were doing aircraft interiors, retrofits, a lot of 747s, L1011 interiors. And eventually they moved, as you know, into the Bellingham area back in 1990. So I was in the first group of people that moved and vacated that facility on Woburn when it was built. And stayed there until 2000. And then I started my own company. So in that ensuing period when I came up here, I was asked, did I want to become a DER? And I had no idea. I mean, I'd worked in interiors and I'd worked with the FAA and the CAA on flammability issues. I'd never really considered that path. So I'm sure all of you know what a DER is, a FAA Designated Engineering Representative. So I can act on behalf of the administrator. And my focus was going to be flammability. So I went through a 2-year mentorship with another DER. Actually, Ada Jamka was a Japanese guy, and he basically taught me, and I watched tests with him, and we worked through test plans and approvals together. And back in 1994, I got my DER ticket, which obviously almost 20 years ago now. Anyway, that got me into flammability. I witnessed many, many tests over the years and decided that I could do a better job of making the equipment. And so when I left and formed my own company, Marlin Engineering, eventually I got into designing test equipment. The FAA has specifications for the equipment, which are in the regulation. So we can't change that, but as far as how you put the unit together, the features you can add that make it more repeatable, that's what I did. So we have a shop in Bellingham, and for the last 20 years we've been building equipment, selling it all over the world. We've got customers all over Asia and Japan, China, South Korea, Philippines, Thailand. In Europe, I got Germany, Austria, Sweden, Switzerland, France, England. So I have a large customer base, and Boeing and Airbus both have our equipment as their standards, so we feel pretty good. And there's only 4 companies in the world that do this equipment, and we've outsold our competitors in FAA equipment. Obviously, other industries have flammability also, buildings, cars, trains, boats, they all have their own regulations, but they have different tests. And I don't get involved with those tests, I just want to focus on the aircraft testing. So anyway, a bit of background as to why we're going to talk about flammability today. Yes, Dave?
Quick question on the DER credential. Does your DER authorization from the FAA, is it limited to a specific area?
Yeah, certain regulations. So Part 25, 853 is flammability of aircraft interiors. There's some others, 856 for cargo liners, so I have that on my ticket. Fire containment, which we're going to talk about, is a different part of that as well. But my main focus is aircraft interior materials. So the things you see when you sit on an aircraft, on a commercial aircraft, yes.
And what was DER again? Would you say that slowly?
In English, I'll say it in American, sorry. Sorry, I understand. So it's a designated engineering representative. So basically the FAA authorizes certain individuals to act on their behalf. So because the FAA doesn't have enough staff to review every piece of data, so they delegate that authority to individuals that they trust. Like I say, I had to do it.
That's like the Boeing Max, by the way.
So it's true. So since I became a DER, the FAA has actually tried to make it better for them or easier for them. So instead of having individuals and thousands of individuals around the country like me, they now authorize organizations. So Safran, who now owns Tecna, they have their own, it's called an ODA, Organization Designated Authority. And that allows them to have like a mini FAA. And they authorize their own people, and they're called unit members now. They're not DERs, but they have the same authority as me, but only within that company. Whereas I can work with any company throughout the country. My designation is only in the US. Although I travel and test at other places in other parts of the world, the authority comes from the FAA. Sometimes they choose to do the testing in other places. At the end of this presentation, I did some testing in Germany recently for a FAA project, which I'll show you. Does that answer your? Okay. All right, so let's get into this. So just a bit of history. Fire safety has been a big focus for the FAA for many, many years. We see the importance of it, make sure that, and the FAA regulations are there to keep safety on aircraft, right? That's the whole thing. And there's always ongoing research being made to try and develop better tests or improve the test. There's in Atlantic City, the airport there, they have a huge technical center, and they have one hangar that has a wide body and a narrow body aircraft that they set fire to, that they can check what happens when a fire, mainly is outside the aircraft, and that's their big focus, is fires that happen when a plane comes in and catches fire. We'll talk more about that in a bit. But
those FAA facilities?
Yes, yeah, it's huge. They have huge pavements there that they test all different pavement materials. They put undercarriages bouncing up and down on it to check. It's a huge technical research center. Atlantic City of all places. So we love going to conferences there, right? That wasn't what I wanted to do. Okay. Obviously, regulations promote safety, and there are two areas that we're going to talk about: in-flight fires, and making sure if a fire occurs on an aircraft in flight, that the fire does not go anywhere, or is contained, and then fires that occur after accidents, and we'll talk about that as well. So there's two definite areas of concern or tests that we take care of. There's regulations, and you can all have a copy of this. I'll give it to Bryant, and you can put a link on the website, and anyone can see this presentation. Okay. But that gives you a history of how tests over the years have evolved. Initially, we started with a very simple Bunsen burner, but over the years, as more, unfortunately, accidents occur and lessons are learned, we developed new tests to overcome what was maybe missed when the aircraft was first designed, and we'll see a bit more about that as well. But you can see there's a progression of tests and what tests came into play. There's a little timeline which you can't read from here, I guess, but anyway, that shows you how we've had tests, we've had incidents, and then tests have come about from that. So the tech center is the people that develop new tests based on what they see as a risk.
What's the radiant panel?
That's
for a type of test?
Yeah, it is. It's a test for insulation materials, and I can go through more on that. I have some images or videos of a test being carried out, but it was, and we'll see also, it was due to the Swiss Air accident that happened. That invoked a lot of research into the insulation materials that are used on the aircraft, and it was found that the test that was currently being used wasn't stringent enough, and so materials that passed a very simple test in a real fire on an aircraft, they burnt. And that's what actually caused the downfall of that Swiss Air aircraft.
MD-11 or what?
Yeah, there's a DC-10, it was a DC-9 MD-11, yeah, one of the two.
Is that an overhead fire in the cockpit?
Yeah, and I have quite a good history on that as well coming up. So the FAA is looking to actually simplify some of the regulation. The regulation over the years has grown, and they've added bits, and it's not very user-friendly, I guess, to the outside person. So we're trying to put together a simplified code and totally redo the 25853 is a federal rule that is, like I said, is based on flammability. So now we're going to have 3 threat-based: in-flight, where you can access the fire; in-flight, where you cannot access the fire, which the insulation is one, because it's above you, you can't see it. But if there's a fire there, that's probably worse than a fire you can reach in a galley. If there's an oven catches fire, at least you have a fire extinguisher, you can put it out. But if it's inaccessible, either in the overhead or in the cargo area, you don't see it. So you want to make sure that those areas are more strictly monitored as far as the materials. And then the post-crash, which we talked about. They're hoping to get this rule out this year. It's been going on for many years, but I think we're pretty close on getting a new regulation. So any questions on that? So what I'm giving you today is a presentation I give to a lot of airlines, manufacturers. I have a training course that I go around the world. In fact, I've been to many countries to present this. So I ask for questions. If you have any questions, yes.
Does your flammability stuff include noxious gases given off by the flames?
So the question came up earlier on. Yes. So the FAA does not have rules for toxicity. Airbus and Boeing internally do require that materials are tested for toxic gases, and we test for carbon monoxide, carbon dioxide, sulfuric materials, HCl, hydrogen chloride, hydrogen fluoride. So there's 5 gases that are tested, but only internally from Airbus and Boeing. The FAA doesn't consider that toxicity is a major contributor to someone dying on the aircraft. That you'd put the fire out. If you can control the materials, then you won't have that hazard anyway. But so yeah, there is some thoughts to toxicity, but not from the FAA, not from regulations.
Does your equipment test the toxicity?
We have equipment that tests toxicity for those people that want it, yeah. We can provide a kit where you can extract the gas at the end of the smoke test, in fact, and then analyze it with various methods. We use Drager tubes, which are colorimetric tubes filled with a material that change color as you draw the gas through. There's also gas analyzers that do it automatically. So yeah, so we do that equipment as well. Yes?
When and if they do phase in these new regulations, how then do the airlines comply with them? In other words, how do they switch over, whether it's just the testing or materials?
I guess the new requirements are not going to change any of the testing that's been done. We're trying to clean up the regulation so it's easier to read and is focused on the various aspects. So there's nothing new that's all of a sudden going to change everything for the airlines. And the airlines are very good at wanting to make sure the aircraft obviously are safe. So they're always at the forefront of making sure that the materials they put on the aircraft, be it galleys or seats or new stow bins, whatever, meet those requirements. They're very good. When you work with the airlines, they want to make sure it's good. So it's not going to affect it, yes.
One other question.
Yeah.
The changes that are coming, will they affect the nature of your equipment? Will you have to modify your systems and procedures to...
Not modified. So there are 2 new pieces of equipment that have been introduced as part of this test. As far as the new regulations, and we've already been building this equipment. We've been working with the FAA on developing this equipment, and so that the moment it's going through a round, we call a round robin, where different labs have got pieces of equipment and they're just testing to make sure that the test is repeatable, either within the lab and also between labs. So there are 2 new pieces of equipment that are being introduced as far as this. But the rule will state it's only applicable to newly certified aircraft. So even like the 777X, is it the new one? That will not be requiring to meet these new rules. But if Boeing come up with a 797 or whatever, the next certified aircraft, they will have to. But you can always go back, and the airlines probably will ask that new materials that they introduce, even on the older aircraft, the legacy aircraft, will have to meet those requirements. Once again, the airlines are very keen to make sure the aircraft meet the very latest regulations. So you can go and use the new tests on older materials.
When you're talking about upgrades and restorations of interiors,
They wouldn't have to go back if they didn't touch the aircraft. If they bought a new galley, for example, and it had this new test as part of it, then they would probably ask for that as part of our certification of the materials. One piece of equipment is just a new version of an old piece that over the years we've found it's not as reliable as it could be, so we worked on building a better mousetrap, if you will, and it's far more repeatable, more reliable. So that's just a change in a new version of what's already there. One test is new for wiring, basically, and composite materials. Obviously, when the rules first came out, composite aircraft weren't around. So the FAA's had to develop some tests for composite, not the structure so much, but the composite parts that go inside. There's a lot more bracketry, secondary structure that is now made, where it used to be aluminum. Now it's, it's carbon fiber or whatever, so. Any more questions? I'm happy, you can just interject whenever. I'm more than happy to.
This new mousetrap, is that of your design? Gotcha.
Yeah. Well, I worked with the FAA just one-on-one with the FAA guy, and he used all of my drawings to create the new mousetrap. So all my competitors would have to build a brand new unit, whereas all mine are the same. So that's very good. God, it cost me a few beers, that one did.
You have a patent on that, right?
Unfortunately, I can't patent an FA. That's not possible. So this just gives an overview. And of course, we're talking passenger aircraft. The GA aircraft, there are a lot more simple rules. We just use a Bunsen burner. That's as much as we go on the GA aircraft. But more than 21 passengers, 19 passengers, I guess, becomes a large aircraft. Then we have to follow these rules. So obviously the cargo linings, we have to do tests for the cargo area. This is one of those inaccessible areas on a passenger aircraft anyway. Cargo aircraft have totally different rules again. They have a whole different set of regulations that apply just to freighter aircraft. But for the cargo areas, we have to do the vertical burn and the cargo oil burner, which I can show you some videos of the actual burner we use, which is huge. Unfortunately, I don't have one at my facility at the moment. When I do, I'll invite any of you to come and watch that test and the firing up of that burner. It's pretty impressive. The flooring just has to meet a vertical burn because all heat will go up, all flames will go up. So we only have to meet a minimum test on the floor. But all of the linings, you see the side walls, the bins, any bulkheads, galley walls, all have to meet a more stringent test for what we call heat release and smoke, which we'll go into a little bit more on that as well. So they have to meet, everything has to meet a Bunsen burner test, a very basic test, and that's for the in-flight fires. So you apply a Bunsen burner for 60 seconds or 12 seconds, depending on what material is, whether it's a big panel or a piece of trim, and you apply the Bunsen burner, you take the flame away, and the flame has to extinguish within 15 seconds on an average of 3. We always do 3 tests, and it's the average of those 3. Yes?
Lithium battery carrying, does that change your world?
Oh yeah, oh yeah. And I haven't got much on that here, but once again, we're a test for carriage of lithium-ion batteries on passenger aircraft. As you know, you can carry lithium-ion.
We can be no stone to full 747 lithium batteries.
Yeah, I know. But once again, you have different rules. You can take the plane down. And there's only normally 2 or 3 of you, right? Not 300 on a plane. The FAA, well actually not the FAA, ICAO banned the carriage of spare lithium-ion batteries on passenger aircraft probably 5 years ago now. And so any passenger aircraft, that's why they ask you when you check in, do you have any spare lithium-ion batteries in your checked bag? Because they're not allowed in the cargo hold. Because if one of them does start a fire, then
you guys have to suppose that there's one already in there, because you've seen the amount of people that travel. So I mean, I bet you there's like that 1%er that basically have those, and that's going to go up in the.
It could well do. I'm not going
to prevent for that, right? So
we at the moment we don't, but we are developing. ICAO. I'm part of an ICAO team that's developing a test that is to test packaging of lithium-ion batteries in a passenger aircraft. So we are looking to actually move ahead with that. And it's not that the Uniteds or Deltas want to carry spare batteries in the hold, although we're talking spare batteries where a manufacturer will ship 100 batteries, little cells. But medical devices fall under that as well. So we can't carry spare batteries, and it's mainly places like Alaska where they rely on air transport to get freight in. And at the moment, they're not allowed to carry spare batteries because of the rules. So what we're developing is a test that will allow passenger aircraft to carry spare lithium-ion batteries on passenger aircraft. That's where we're going with this. So yeah, lithium-ion batteries is
so the material. So you guys found a material that's going to be withstanding that intense heat.
We're developing a test to allow the manufacturers we don't define the packaging, but we have a test that they can use to test their packaging so that it is safe to put on an aircraft. Yeah, we're not designing the package itself, but we're developing the test so that we can recreate the conditions of a battery that's going goes into runaway, thermal runaway. We actually incite it, and we put a heater on it, and we make it burn, and then make sure the package will contain that fire. So yeah, so we're working on that as well and I haven't got anything on that in here, but we're doing that test as well at our facility. Yeah, batteries are not good. Ducting in the overhead, that falls under this inaccessible area, and that was part of the Swiss Air issue as well, the ducting, because you got air, you got materials that were not designed necessarily to have a more stringent fire test. They met a basic test that was developed for all interior parts. And when we're talking interior, we're talking the pressurized area, basically. So anything outside on the wing, I don't get involved with that side of it. There are other tests for engines, for the components. They all have to go through tests, and some of them are flammability tests, where you've put an intense flame on a component to make sure it doesn't fall apart and spew fuel or hydraulic fluid everywhere. So there are other tests that are done, but I don't get involved with that side. It's just the interior.
Can we assume there's no significance to the hole in the bottom of your airplane there?
Probably, yeah. I think we're...
That's a dump bell.
yeah.
That's a rainwater.
God, there's always someone in the room, right? So, very simple Bunsen burner test. We've been around for many, many years. This was the first test. Of course, back in the early part of aviation, all the materials were wood, basically. I mean, we had no plastics and aluminums and so on. It was all wood stuff. But eventually we realized that maybe planes do catch fire. So this was the original test. It was a horizontal test. So the test sample was put in horizontal. You put a flame. You applied the flame for 15 seconds, moved it away, and then what you find is the burn would progress along the material. And then you'd measure the burn rate, and there was a limit that the FAA said you can only burn 2.5 inches per minute maximum. If it's more than that, you can't use it.
You mean like Velcro?
Yeah. Well, I hate Velcro.
Have they ever gotten into testing aircraft fabric for wooden fabric? Like dope and this kind of stuff?
No, because that's the fuselage.
Okay.
We only get involved with the interior. Oh, I do anyway. Mm-hmm. I don't know what they ever did with the fabric aircraft, but there's not many passenger aircraft. Once again, they were talking commercial aircraft here, not GA. But yeah, they do go up. You're right.
You keep talking about a Bunsen burner. Is every Bunsen burner that's used in these tests then a minute flame that is a set?
Absolutely. Yeah, so it's a standard Bunsen burner that we all used in chemistry in high school, wherever. It's the same thing. We use methane gas, always 99% pure, because it burns at a very consistent rate. Mm-hmm. We do measure the temperature. It's 1700 degrees, and we have to use a thermocouple to test it. The flame height is very important as well, obviously. So we measure the flame height every day. When a lab will start this test, they'll check the flame is right. And after you've done a few of these, you get to know what that flame should look like. And it impinges right on the bottom. The sample is 3/4 of an inch away from the Bunsen. So it sees that 1700 degrees, very localized. And we burn the surface of the material. So a honeycomb panel that's maybe this thick, we'll just put the Bunsen burner right under the skin. Because typically it's going to burn the decorative or whatever's applied, the paint. So that's what we're looking to test. Yes, Tom?
So a lot of manufacturers typically will have a supplier that they will vet. And they'll have this done, I'm sure, where the materials are tested. And then once they're tested, they can start buying from that supplier. But in the current environment where there's a lot of supply disruption, a lot of raw materials are missing, are you finding that some of the suppliers of these materials are having to get other suppliers, and does that mean they have to get retested?
So typically the manufacturers, like the Safrans and the Collins, they'll buy them raw materials from a manufacturer, and they may have to use different materials, but the way the FAA inspection side, now I don't get involved with the quality. There's two sides to the DER. There's also a DMIR, manufacturing inspection. So he takes care of the ongoing quality. And so normally the manufacturers create specifications, and within that specification there is a test that's required from the supplier to ensure that there's consistency in that material And even if they do change their sub-supplier, they still have to meet a basic specification. But that's just the raw material, honeycomb panel, for example. But when the next level up, the person that's making a galley, for example, when you apply a finish to that, like a decorative or wallpaper or whatever is being applied, we test what's on the aircraft. So we don't use that data from the raw material. We have to test it in its final configuration on the aircraft. We can't break it apart and say, well, that passed and that passed. When you bond it together, it's good. Because the synergy, when you bond things together, changes the whole dynamics of that part. So we have to test it as installed on the aircraft. So
I just had a follow-up question for you. I'm sorry to...
No, that's fine.
So as materials age, certain properties can change. And I wonder, is there any kind of standard out there that requires materials to be tested when they're new and then maybe after a certain length of time?
There is not any requirement at the moment. No, we don't have to go back and retest all materials. And you're right, there could be some degradation in the quality of flammability, but that's not something that is looked at.
So the moral of the story is fly
on a new aircraft. Yeah, you got that new car smell, you good. Although you can go on an aircraft and it could be 20 years old with a new interior and you would never know. I mean, there's we just started a project with United. The first 319s just come off. They've got 150 of these A319-20 models. They put all new interiors, new seats. It'll look like a Max. When you walk inside it, you think, oh, well, I'm in a Max. But it's not. It's a retrofitted, I'm saying Max and 319, that's wrong. But it's got the same look, basically. And you'd never know. It's 20 years old. So, but it's all new materials. That's the good thing, right? So what we're looking for on the Bunsen burner is the flame to extinguish within a certain amount of time. The burn length as well is important. We're allowed 6 or 9 inches, depending on the material. And the drips. Some materials do drip. We want to make sure the drips extinguish, that they don't form a pool and continue a fire, on the ground. So there are we have requirements that we have to. There's a DER I have to watch, and I sign off to say that it met all the requirements. Seat oil burn test. So all the seats on an aircraft. And particularly the foam, because that was a factor for flammability, have to now go through this oil burn test. So this is our fixture. It looks like a seat frame. What happens is, and I got a video of a test actually later on. The supplier manufactures test samples that are built to the right thickness and size. They sit on this frame. That's our oil burner that we talked about. We will see that in operation. And basically, we just heat that thing up and set fire to it. And the requirements are very stringent. We can only lose 10% of the weight of the cushion in this test. And it's a very stringent test. So the seats that you sit on are very safe nowadays. When the rule came in, the foams were not designed for that type of test. So we had to put Kevlar covers under the dress cover and on top of the cushion. And the seats were so uncomfortable in those days. Yes.
So is that the implementation that happened because their seat cushions were flotation device? So
yeah.
You had two world here that you had to roll the dice on to be and say, hey, that has to flow, but yet it cannot burn or.
Right. You got to balance that. I mean, they still got to be. The covers were pretty thin, but the Kevlar didn't allow the flame to get into the cushion to the seat, the urethane foams. Nowadays, the manufacturers of seat foams have developed new materials, new compositions that meet our test and still remain floatable. There's not, I guess it's only the smaller aircraft, the smaller regionals that use the seat cushions. I think all the big aircraft will use a life vest, right? So that probably doesn't matter too much about that. But the key thing is, though, on an aircraft, weight. And so these seat cushions have also got to be very lightweight, or else, you got 100, 200 seats on a plane. Every pound you add, that's a lot of weight that can go onto the aircraft. So the manufacturers of the seats are always looking to make the seats lighter, lightweight foams. I mean, some of the planes have hardly got any foam that you sit on. like Allegiance plane. You just sitting on a. I don't really pick on Allegiance. I flew them last week, and I like Allegiance. But
What's the fuel of this test?
kerosene, Jet A fuel.
Yeah, okay.
They can use diesel, anything that's of that nature,
Yeah.
but diesel is just black. It's horrible to burn. Kerosene is a bit nicer, and it's very consistent. So I go to, when we're doing testing, I have to go with my 5-gallon cans out to BAS, and they look at me, you want 5 gallons of Jet A1? What are you? Yep, it's okay. Do you have a tail number? Yep, I got my tail number. It's pretty funny. They know me there now.
You can whip out the FA license.
That's right. Yeah, I'm certified. Yeah. I just give them my Osprey tail number and say, yeah, but that's got a regular engine. Yeah. Sorry. You had a question? Any more?
You're using diesel in a piston engine?
Sorry?
So they don't ask if you're using diesel in a piston engine?
No, they don't. Okay, so we'll see more of this. I just want to give you an overview of the types of tests we do. That's the same burner, but now mounted vertically, and this is for testing the cargo liners that you see. So up the top is actually, there's a panel up there that's about this by this, and we put the burner on for 2 minutes, and there can be no penetration during that 2-minute period. The flames go around the outside, they lick around the outside, but no physical penetration through the liner. That's the test here. There's also a panel you can see behind. This is testing the sidewall of a cargo liner. So the ceiling is the more critical, because obviously above it there's a lot of controls, wiring, and so the burner, the liner that can be used on the ceiling can also be used on the sides and the floor, but not the other way around. If you only test it for the sides, you cannot use that material on the top. The materials are just a laminate as well. They're just a phenolic laminate that's used up there. Probably, I don't know, 1/10 of an inch thick, but it'll meet that test easily. It'll burn aluminum right up. So all of the materials that are used for joints typically have to be stainless. All the bezels that are used for lights or for any penetrations are normally stainless, because the aluminum will just burn away in that flame. It's quite amazing. Okay, moving on.
You tend to get more heat concentration where the vertical meets the horizontal in that corner.
It probably is, but you'll mimic the joint that goes between, that's actually in an aircraft at that point. So you'll look for that joint. Yeah, it probably does, because obviously the flame's got nowhere to go, so there's a lot of intensity in that point. Yeah. Okay, the OSU heat release. This is to do with the heat that's being generated at a post-crash fire, and you've got a plane, the flames outside the aircraft. You want to maintain an area inside the aircraft where passengers are allowed to escape from the aircraft without the fear of the heat being generated by burning. The plane's going to burn. We can't stop that at that point. But we want to create an environment the passengers can escape off the aircraft. There's a 90-second rule that the airlines have to meet, that the manufacturers have to meet to certify a particular configuration. We push that envelope a bit more and say, okay, we've got 5 minutes. We'll provide an environment for passengers that won't get burnt from the heat of the flame outside. And we also do the smoke the same way. We have to do a smoke and a heat test at the same time. And that's for large interior passenger surfaces. So the sidewalls, the bins, the ceiling, bulkheads, any large surface can emit quite a bit of heat from burning. So we want to keep that heat down. Because what happens eventually is you'll get the flashover occur when you get all the right materials at the right, the chemicals that are being off-gassed, and you get a flashover. We want to get people off that plane before that occurs. That's the whole intent of this test. OSU was designed back in the 80s by Dr. Smith at Ohio State University. That's why this test is commonly known the OSU test. It's developed by Boeing, Airbus, FAA, and Ohio State. And they come up with this tester. And this is the one that's now been the second generation. The new mousetrap is being replaced by a new version of this. Back in the day, the drawings were very basic. The people could make these machines, and there could be a lot of variation. But now we're focusing on making sure that the materials, that the dimensions and the specifications are very, very tight, so that we can repeat the test. So, and I got some videos of this later. Smoke chamber, like I say, that's tested as well. So, and this stems from a big accident that occurred in England back in the 80s, and we'll talk about that. The British Airways, British Air Tours, I think it was, a 737. That brought in a lot of rules, and we'll talk about that.
Yeah, most
Smoke
of
was
the
one of
people
them.
died of smoke inhalation, didn't they?
There was, because the materials used on the interiors up until that point were epoxies. And they just burned and smoke, and people couldn't see to get off that plane. That was one of the things. That's where escape path lighting came in, minimizing the amount of smoke by using low smoke materials. So this was what the test. Materials nowadays easily meet this requirement, but the epoxies definitely didn't. Radiant panel, David asked about that. So this is to test insulation materials that is behind all the sidewalls in the ceiling, and it's used for thermal or acoustic reasons, or both, to prevent the noise from the outside of the aircraft, and also to prevent the cold skin. So you've got at least the sidewall, you can touch it and not get frozen. So there's thermal and acoustic insulation. It is basically just 1-inch fiberglass, but the covering that's on that, once again, weight is a big thing. It's covered with a very, very thin mylar material, and it's totally sealed. All those blankets that we call them blankets behind the sidewalls are sealed around all the edges, because going up and down, you get moisture, you get condensation, and if you didn't seal the bags, they would just wick all that moisture in, and the plane would be twice as heavy over a few years, right? So we want to make sure those blankets are sealed and covered. Well, the material that was used, once again, met a very basic Bunsen burner test, but in a real environment where in the overhead, the flame just spread along it. And this test is for us to measure how much flame propagation there is, and that's what we do with the radiant panel test. Yes.
So I'm sure, because things always, so they say, things are always improving, trying to make it better, trying to make it better. So are you encountering a lot of the manufacturer coming to you and say, hey, we need this to be tested to be approved so we can sell it to the airline? Are you getting a lot of new ideas coming from the woodworks?
There's always new material. People think they've got the best material out there, and we have to test it before it can go on to an aircraft. But we do a lot of research testing. Where someone comes and say, hey, can we try this material? We don't have a test lab here in Bellingham. We just provide the equipment. But there's other labs that I can point people to and say, oh, there's a lab in Everett that's got this radiant panel. We'll go down there and have a test done, and I'll help them, develop materials, or look at how it burns and give them feedback and say, hey, you need to reduce that propagation. It doesn't meet the requirements so far. But yeah, manufacturers are always coming up with new things. So
The requests for testing, they typically come from the materials manufacturer, the airframe manufacturer, or the end-use customer, or
the material manufacturer is the main one, because they're trying to develop new materials to sell to the airlines for their new interiors. There's a material that's out there now. It's been around for a few years, ultra leather. So it's a synthetic leather, but the consistency of it, it varies, and so we have to test. That is tested each batch. We have to test that because there are inconsistencies in that material. But there's a good example of a material where manufacturers develop this new material that replaces leather. It's cheaper than leather. It looks like leather. It feels like leather, but the burning characteristics are totally different. Funny enough, cows don't burn very much. I can tell you that. I've seen, they smell awful. It's the
With the methane gas, it could be an issue.
Yeah, with the methane, it definitely could. That combination. Okay, I've got examples of this test as well. I can show you videos. And then we have a burn-through test, which the FAA developed. So imagine a fire outside the aircraft. The insulation materials in place are along the bottom part of the aircraft, it was around the whole aircraft, but particularly down the bottom end. They decided that we could use that material to actually prevent fire from coming into the aircraft if there was a fire outside. And so now the manufacturers have to prove that the system of how they overlap all of the insulation blankets, and you can see that's a mock-up of a fuselage with the insulation. The burner is pointing at it, and once again, it's a 2-minute test, and we have to make sure that no flame will penetrate through the insulation material. So not only does it have to meet a propagation test when it's used inside the aircraft, but also the aircraft manufacturers, the airframe manufacturers, have to prove that their system prevents burn through of that. We don't use aluminum on there because the aluminum just burns right away. But this material holds up pretty good, and it acts as a barrier to prevent fire from coming into the aircraft.
Is it Nomex or what is it?
No, it's just Mylar with fiberglass.
Polyester?
Yeah. And it's mainly the fiberglass that's going to act as that barrier, but it's only normally 1 inch thick. But you have to design it such that all the joints are overlapping and clipped, and it's not just putting blankets in. You have to make sure it's all totally a system that's on the aircraft. Yes.
So it's not the same materials like when you have the laptop, when you have the laptops on fire, you put this in an envelope. It's a different material.
It's just this is just a regular, almost a household fiberglass that you buy. It's a 1 inch thick fiberglass, but it's covered with a very thin Mylar. I'll try and bring, in a future meeting, I'll bring some of the samples. I should have brought some to show you what these materials are. Dave's obviously confirmed with some of it because he's worked in, you've done the sidewalls. We normally bond the insulation on the back of the sidewall. But this test is only for the cheek area, the lower part below the floor. It doesn't apply above the floor because we're looking for flames that are coming in from a fuel fire outside the aircraft. Okay, you've already asked too many questions. All right, so what I want to do now is this lesson learned is it'll show us how tests became into being because of accidents, and then I can show you how by introducing new materials we've actually made the planes a lot safer even though they burnt up. So hopefully you find this interesting. So once again, I'm not going to read through all this. You can have this presentation and read through it, but this is a significant one, happened back in 1980, LT-11 in Riyadh, full of pilgrims. There was a fire indication. The captain decided to abort. I think he aborted the takeoff, but he didn't evacuate the aircraft. And basically everyone died on that plane on the ground. And he didn't it was a cargo fire below the floor, and the materials allowed the fire to come through at that point. It says all 301 passengers and crew perished in the fire. There's a picture of the aftermath of this. But it was on the ground. It was stationary, which was the incredible thing. And the captain, for whatever reason, did not initiate an evacuation. But what this did is it created tests for making sure that the linings didn't allow flames to penetrate. In flight, on the ground, it shouldn't have been an issue. They should have got everyone off the plane. But if you have a cargo fire in the air, then those materials should allow a fire not to escape and allow the pilot to find a suitable landing place pretty quickly. And obviously there's smoke detectors, there's fire detectors, and there's some fire suppression in in the cargo hold anyway. But nevertheless, you don't want a fire to start in an area that you can't get to. British Air Tours, this was a very significant incident that created a lot of rules that came out from this. Basically, once again, this is a ground-based accident. 737 had an engine failure on takeoff. He aborted the flight, the takeoff, pulled off the runway. It was the left-hand engine that what happened was, and I don't know if you're familiar with the GT8 engines, they have a series of combustion cans around the periphery, and they obviously have a lot of stress because of the heat, and they get repaired. The manufacturer has a repair scheme. Well, there was a bad weld, and basically it exploded in one of these cans. It just happened to be, if you're looking behind the aircraft, it was about the 2 o'clock, and it actually let go, went through the engine casing, or the outer casing, and just happened to hit one of the wing access hatches, the access points on the wing, on the lower part of the wing. and went through that, and obviously fuel came out, fire erupted. He put the reverse thrusts on to slow the aircraft when he did the abortion. And I know on the old 737s, the clamshells, but they're not like this. They're like this, right, on the side. And it forced all these hot flames onto the side of the aircraft. He also happened to pull off, and the crosswind. Everything went wrong. Everything that could have gone wrong on that particular flight happened. All right, so there was an evacuation ordered, obviously, but the back end of the aircraft was horrible, and it had the old materials. It had materials that would drip, would create a lot of heat. There was smoke, seat cushions burnt. They couldn't find their way off at the aircraft. Escape, the access area around the doors was limited. Escape, the overwing exits were very close. And so many rules came into play after this accident. We had new interior materials where we went from epoxies to a phenolic material, which is a very low heat and smoke. Seat cushions changed. Escape path lighting came in. Access areas around the exit doors, so there was always a place for an attendant to stand by so you could have egress. There was never that space, everything was tight. Overwing exits, we had to open up that gap to allow people to get through an overwing exit. So many rules came into play just because of this one incident. So that was the aftermath of the interior. It was it's a bit grainy picture there. That was the back end of the aircraft from the right side. So you can see the whole back end just melted. But there's a good picture of what I was saying. So you can see the thrust reversers here and how they're angled. So it just deflected the engine. This is the engine that had the problem. Under the wing was where the fuel dropped, and it just pushed all the flames on the side of the aircraft. I forget how many. Let me go back up here. 57 passengers perished on this. And once again, I'm not going to read this, but you can read it at your leisure. There's actually at the beginning of this section there's a web link, and this is all public. You can always go to this particular website, an FAA website that gives you all the information on all accidents. But if you type in flammability or fire, it'll actually just focus on the fire-related accidents.
Have they changed the orientation?
Well, the new engines just have sliding ones. The old 200s still have them. I mean, if there's any of those still flying, I don't think there are.
No, they have a noise problem, so they...
Yeah, the JT8s were all gone. They were changed to CFMs on the 300, I think. Yeah, it was only the 200s that had these. And well, it wouldn't apply to a 727 had the same, but engines are way back there, so it didn't matter. So yeah, these are the rules that came in following that particular accident. And then the Swiss Air one. This is obviously more recent, MD-11, bound for Geneva. Basically what happened, and there's a great Nova movie, TV program about the investigation into this, but they actually found one wire that had been bent over and had, it was the wrong wire, it was too tight a bend, and you would appreciate this. It arced, and this started the whole chain of events. It was behind the flight deck. Basically what they'd done is installed a new IFE system, secondarily as an STC. They manufactured the STC holder in California that designed the system, called out the wrong wire, called out for too tight a bend, and that started the whole thing. Well, I know you don't have IFE on your plane, so it doesn't matter. The flight deck had no way of turning off the IFE system because it was hooked into the main bus. And so now there's a rule that says there has to be, the captain has the ability to just cut that. And it's on a non-essential bus now, it's not on the main bus. So there are other things that happen because of this. We should have done that, you know. But what happened was that fire started right behind the flight deck, and that insulation material was what started to burn, and it just propagated along the surface of that mylar and went all the way along the aircraft. The flight deck had no idea what was going on. until they started losing systems because the wiring was now burning. It got into the air conditioning ducts because there's air flowing through there, so it's nice fuel to keep that fire going. And unfortunately, the plane went down without them knowing why.
My understanding, Joe, is, correct me if I'm wrong, please. My understanding is they could have made a rapid descent.
They could have, if they'd have realized, if they'd have known, they could have made it to land. Yeah, and then there's been many simulations done that if they'd have known right away, they could have made it back. They weren't that far off the coast, but they carried on.
Weren't they burning off fuel? Wasn't that part of it? Extending instead of making a quick landing, I thought they were burning off fuel.
They didn't know. No, they just carried on until there was a point where the plane's going down. They had no idea why.
Okay.
They may have started to turn back. I don't know, but I don't think they were.
No, they were carried on. They did not even, they just carried on.
So, like I say, I'm not going to read through all this, but it gives you an indication of what happened was. They actually brought the plane back up and recreated the plane, and that's when they found where that problem was, which is amazing, the investigators, how they can go to that finer detail and find where the problem occurred. This created the insulation, the radiant panel test that we use for insulation now. And now we're working on the wiring and the ducting to make sure those materials, is that bad? Jeez. They also meet, because anything that's in that overhead area, we want to make sure is very fire hard. That's not, if there's a fire, it's not going to create a path of fire to extend down the aircraft. So, all right, results. This is the good bit. So, back in 2008, we had a Continental 37. Denver took off in a strong crosswind, and it veered off the side of the runway and crashed to the side of the runway and broke up. Everyone escaped, only 38 injuries, but that was the aftermath of that plane. Very similar to what we saw on the Air Tours plane with it burning. You can see there was a fuel fire. It was full of fuel. Obviously, it was just taken off. And there's the back end of that aircraft. But everyone escaped from that plane. But this had new materials. So the evacuation was no problem. Everyone got off. An Air France 340 at Toronto. Back in 2005, it landed in a full visibility and went off the end of the runway and stopped in a ravine, caught fire. Once again, everyone escaped off this plane. 297 passengers, 12 crew. And that was the plane on fire after it went off the end of the runway. And that was what it was like when it was finished. As you can see, we're not going to save the plane. That's not the intent of the testing we do. And then more recently, we had that Aviation flight back in San Francisco. Landed short, hit the wall as it was landing at San Francisco's airport. And there, obviously, we call it a survivable accident, where it's not crashing into a mountain. If it like this is a very survivable accident. I mean, there was no reason for people to perish because of impact. Although the plane spun around a few times, the G-forces weren't enough to cause any injuries or deaths, any fatalities because of that. But everyone could have got off that plane. And you probably remember and you can see, it totally burnt out. There are tests as well that came from Manchester, the escape slides. Some of the escape slides burst on the Manchester accident. And so now we have more stringent tests for the escape slide material. You apply a heat source to that and make sure it doesn't puncture or catch fire. So that's obviously, you can see there, that I don't know why it deflated, but anyway, you can see the aftermath of what happens inside the aircraft.
Excuse me, that was the San Francisco incident.
Yes, yeah. And you can see there was obviously the seats were around, but passengers didn't die or from impact. That was the important thing there. But when it did catch fire, it caught fire. And we're never going to stop.
Like density, like the high density seat, the one that's like smaller.
I think so. Well, it's an Asian plane. It's going to have lots of. So no, I'm not. No, they're standard seats. But yeah, it was a high density. The Asiana plane, I think, was pretty.
Flown by 2 senior pilots and a Cheshire.
Saving.
Yeah, there was. Yeah, you're right there. Anyway, so I guess the point is that by introducing these tests that we've developed over the years, unfortunately, because of accidents, now the planes are definitely a lot safer. We haven't had to go through this recently at all. I can't remember any recent accidents that I can put on this slide. That was the last major one that happened. Okay, you all good? Mm-hmm. All right. So now we're going to show you some more in more detail some of the tests. Methane gas we use. We set the flame height. Criteria 12 or 60 seconds depending on the material, and we have press criteria. That's my flame chamber that we use. We measure the flame height with a little gauge, make sure the height of the flame is consistent for the Bunsen burner test. And now I've got some videos. So that's the Bunsen burner coming in. So this is orientated vertically. And you can see we set fire. It stays in place for either 12 seconds or 60 seconds depending on the material. That's what we want to see. We want that thing to go right out. So that's a good material. Okay?
But there's no standard with respect to the combustion constituents?
No.
Whatever comes off of it is okay as far as the...
And this test, yeah. So this is for interior in-flight fires, and that's where the toxicity would be tested by Airbus and Boeing. But it's not considered to be a major cause of a death or a fatality in flight. Yes.
Seriously, this little flame can actually simulate the same thing as a thermal runaway?
No. This isn't for batteries. This is just...
No, but I'm saying it's going to react to that, that kind of intensity of the heat. That's going to react to any kind of interior of an airplane. So is that 1700 degrees standard, or is that basically takes in effect the lithium ion that burns?
This test has been around way before batteries were ever put on the aircraft. But so if you're storing lithium batteries, or they used to have those digiplayers where they had batteries in, and they used to store them in a cabinet. That cabinet had to be tested like a cargo compartment, so it didn't burn out. So there are requirements if you have batteries that are stored in the aircraft. But this is just for materials. We're not looking at batteries at this point. That's a whole other ballgame.
I'm thinking material reacting to a thermal runaway. So I'm saying, is that a different flame? Is that a different equation altogether?
Yeah, it must be. We don't even consider what that intensity would be. I understand what you're saying, but we don't test for that necessarily. We're looking for ignition sources that may occur in flight. Be it, obviously people used to smoke way back. That's all stopped, but that could cause a fire on an aircraft. You could have fires in a galley. Galleys are probably the most area where you get most little fires, from an oven or a boiler, because there's a lot of wiring in there. It's mainly a wiring thing. But all materials have to meet this test. Now, batteries, we haven't changed the rule because of batteries being on board aircraft anymore. With the laptops or chargers or whatever. So, but hopefully there are other methods in place with the flight crew that they can put them into bags, or they have procedures that they have to follow. Nowadays they do. Yeah, but this is just a basic flammability test that we're doing. So this is another material. This looks like a plastic, and I don't think this is going to turn out good. Once again, flame just applied for 12 seconds. It is 1700 degrees right at the point where the ignition is, although albeit small. But you'll see here that this material is not going to self-extinguish. It's going to carry on burning. It's going to get worse. Now we're getting dripping.
What was the material?
I don't know. It's a plastic material, probably a PVC. I don't know. Now this material would not be allowed on an aircraft. This fails. So I would never be able to approve a test report that had this material because it failed. So that material would never appear on an aircraft. Yep, this is getting worse. Okay. So that's a failure.
The little chambers that you have, do you pressurize them the same thing as an airplane?
No, it's not pressurized. No. I mean, although it's pressurized to an equivalent of 8,000 feet, we don't
You don't simulate that?
No, at
Yeah,
all.
it would be, but it would be less of a problem at 8,000 feet. 'Cause
There's less air. The air density is so much lower that I don't think that would be necessarily a problem. Yeah. The horizontal test was the original test, like I said, about propagation of the. Oops, shoot. I think I got a video of that one. Yeah, let's just watch that. So this is used for. There are some materials on the aircraft that have to use that material, like acrylic. We use acrylics on the aircraft because there was a good vision. So like on windows on the side, we have to use those materials, and then they will not meet the vertical burn test. But because it's a requirement on the aircraft to use those type of materials, we do test, but it's a less stringent test. But everything on the aircraft has to be tested. You cannot put anything on the aircraft other than pillows and blankets because they're not part of the original equipment. But you can see here, the flame is slowly moving along that material. I believe this one would pass. It's a very slow burn.
We pre-measured this, so I did this one.
Sorry for the commentary in the back.
Tell me when you want them to start.
Anyway, you can get the idea, the vertical test and the horizontal test, okay? Well, that one actually went out. That was a pass, because it didn't propagate at the speed that we're allowed to go by. Okay. All the wires tested currently with the same test setup, but the burner is orientated at 6 degrees, and you can see the wire. I'm pointing to the screen. I'm up here. So here's the wire. We have our weight on there just to keep it taut so that it doesn't bow out. And then the burner is impinging on the side of the wire. And it's applied for 30 seconds, and then we pull the flame away. And there's requirements for extinguishing time and burn length. Now, all aircraft wiring, the MS wiring that's used, easily beats this test. But nowadays with IFE and they want to use USB cables, and we have to test all of it. Any wire that goes on the aircraft has to be tested. And it's certainly on the commercial wires, it's sometimes a hit and miss. But you have to test everything. You see that was easily a pass.
And it's at 60 degrees, there's not a vertical or horizontal?
No, this was the test that was developed. Yeah. Sorry, Dave, you got a...
I was just going to ask, is there, are BIS jets, are they certified to the same standard? Do you have to do the same sort of testing?
All the ignition tests are required. Not heat and smoke because of the smaller passenger count. The only reason for the heat and smoke is if you have a large number of passengers, or more than 19. And the executive jets, I mean, even a 3-7 executive, they don't have to meet heat and smoke because there's so few people on board. They can egress off that plane easily within 90 seconds. So there's a rule that the FAA has that allows executive jets or business jets, whatever you want to call them, VIPs, to not have to meet the heat and smoke because they have materials on board those aircraft that will never ever meet heat and smoke. We've tried. I work with a company in Everett, Greenpoint, and they commonly do these VIP interiors, and we've done challenges on different materials. We had a 767 they converted into a casino. And the front end was a casino with gaming tables and a bar, and the back end was all passengers, so that when they were flying, the passengers could take off and land. But because there's so many people on board, the FAA said, you need to meet the full rule. So all of the fancy materials in the cabin for the casino area, we had to meet the stringent heat and smoke test, which was a challenge because they wanted all these fancy fabrics, soft touch. There was foam behind them. But we made it. We got it through. But a lot of testing, a lot of experimentation on that. But the business jet, the wiring is the same for all aircraft. You should. I think we mentioned the wire that you use. That's all MS wiring, right? You don't use any commercial.
Well, with the exception of the
very small links, maybe, or
the big wires, the primary power wires. Those I use marine cables.
Yeah, but the thing is, a big heavy copper cable, that's not going to burn. It's the insulation on that is what we're testing, and there's so much heat being sucked into that big cable, the outside's never going to burn. Trust me. I've done a few tests. All right, heat release chamber, we've been measuring how much heat is generated in 5-minute tests. And we actually are building a new one of these, and I will once again invite you to see this test when we're have it ready to go. This is our unit. It's basically a chamber and a control panel. We have 4 glow bars that are emitting a large amount of energy, heat energy. We inject a sample and just set fire to it with a pilot, and the front, because of the heat, the front of the surface will just burn, and it'll emit an amount of heat, simulating what would happen in that environment where you've got an outside fire, a lot of heat, and one ignition source, and you want to know that it's not going to create a lot of heat that will create that flashover. That's the whole process that we're doing here. I think I've got a... So there's a sample being inserted. It's a 6x6 sample, representative of the side wall or a galley wall or whatever. There's the pilots that we set fire to the surface. The sample gets injected. And we're measuring the amount of heat that's being generated. There's air actually coming through that stack. And so there's thermocouples on the top that are measuring, monitoring the temperature that's being generated before the test. And as the test occurs, obviously there's more hot air coming through, which increases the temperature on the top. And that's what we're monitoring to know how much heat is being generated by this burning on the surface. The honeycomb panels typically don't burn very much. They're very, very low, but it's that front surface, it's the adhesive, bonding the decorative or the ultra leather or whatever the side of the materials that you see. Anyway, that's our...
Did they change the construction of the honeycomb, or is it still the same material, or did they change it like the technology?
Oh, yeah, over the years, or when we had that accident, the British Airways one, right, the old materials were epoxy resins that we used for the fiberglass. Nomex core didn't change, but the resin that impregnated the fiberglass on the skins, that was an epoxy, which is very good strength-wise, but horrible in smoke more. So now the manufacturer have moved to a phenolic-based resin, which isn't quite as strong, which means you have to engineer the parts a little bit differently, but they meet the heat and smoke requirements. So there hasn't been much progression following that materials, because why develop something when it already meets the requirements? So there probably are people that are researching new materials. Some of the panels have been replaced by new foams that are lightweight, that meet these requirements, that can be pressed into shape. But most of it is all honeycomb. We use some metal honeycomb for highly stressed parts, bulkheads where the flight attendants sit on, because that seat has to stay in place. And so we have used metal honeycomb for those bulkheads normally. Obviously they don't burn, but the heat release, funny enough, we have issues because the resin in that bonds the core to the metal skin is an epoxy for strength. And if the heat gets through in that 5 minutes, we can have some issues, but we have ways to overcome that. We can put insulators on and to prevent the heat getting through. There's a lot of tricks is not the right, solutions. A lot of solutions we've developed over the years to overcome problems that we see with some materials that are required to be on the aircraft but don't necessarily meet the rule in a very basic form. So we have things we can apply to overcome that. That's just a picture, I think, of the... Yeah, it's just... this is probably showing it burning. That's probably a failure. I'm going to say there's a lot of heat being generated there, but... But once it's burnt off, the test just burns itself out. Let's move on. Smoke density, I'm going to try and get through this. I want to get to the end because I think you'll find the end interesting. Smoke density, it's a similar type of test. We have a heater and a smaller sample, 3x3 of the same construction, It's, whatever the bulkhead or the sidewall or whatever the material we're testing is. And we put that in front of a burner, we set fire to it, and the chamber is 3 by 3 by 2, sealed, and basically we keep all the smoke inside the chamber, and we measure how much intensity of the smoke by a light source. We have a light underneath with a beam that's coming through the chamber, and we measure it with a photometer on the top. And we start with a clear chamber, so it's 100% visibility, and then we block the light off, and we set the machine to say that this is totally black, that you cannot see in the machine. So we have a range of 0 to 100. When we set fire to the chamber, to the sample, it builds up the smoke inside the chamber and then obscures that light beam. And that's how we measure how much smoke is in the chamber. So we can look at the intensity. And there's a limit that the FAA set through their research. It's tough to see in videos. Once again, if I get a machine that I can show you.
Is that similar to a photoelectric smoke alarm?
No.
Household type stuff?
The lighted ones, yes. But there are different types of smoke detectors. Photoelectric one, yeah. It's looking for obscurity, yeah. Mm-hmm. You can't really see it too much, but that's the sample you can see burning off, and it's giving off some smoke. But it'll fill this chamber up, or not, hopefully. I've had it where I'm looking through the window, you cannot see it anymore, and that's not good. But this test is for 4 minutes. And then if we're doing toxicity tests, at the end of this test, we extract the gas from here, and that's what we use to measure the toxicity of the gases that are being generated when this thing burns. Okay, flame propagation. This one's a more exciting one. Have a big radiant heater, and the idea is you're applying a heat source and then ignite the surface to create the burning. So you saw we had the big glow bars on the heat release. We had the little furnace for the smoke, and this is the heater for the radiant panel. This test was developed for carpets, not even for aircraft. It was a test that was measuring how much flame propagation on a carpet. So we've used that tester as the FAA did, to base it. So this is typical insulation bag material. There's the mylar, the yellow mylar. So we have the radiant panel you saw there. We have a pilot flame which ignites the surface, and we're allowed 2 inches of burn and 2 seconds after flame when we remove the burner, and it's applied for 15 seconds.
Is all this test equipment stuff that you make?
Yeah. So you can see they went out immediately. That's a good material for insulation on the aircraft. Okay, so that was a good one.
Are those slits in the bag?
It's to allow the air to escape so the bag doesn't pillow up, because it's not adhered in there. So this one is not so good. I'm going to just show you the difference. This was one of the original mylars that we used, and you can see the flames propagating along, and this was the cause of the Swiss Air. So it just propagated along the surface of the mylar. Fiberglass doesn't burn. It's that surface that's causing the problem.
It was metallized.
Metallized polyester, yeah.
Metallized PET, I think.
Yeah, you're right.
And is that what this is?
This one is, yeah. Yeah, you can see it's got that metal finish to it, that very thin. It's a very, very thin mylar, like the mylar balloons. I mean, it's a very thin material. But that one, that was a fail. All right, it didn't go all the way along, but it failed the criteria of the 2 inches, 2 seconds rule, which is what the FAA set as our criteria. And this is one that you don't want to see on an aircraft. We were given this by a manufacturer in England that wanted to put it inside it was an oven. But because it was insulation, we had to test it, even though it was inside the insulation of an oven door. Yeah, this was not good. To the point we had to actually put it out with a fire extinguisher. Seriously, that never got anywhere near an aircraft. Trust me.
During flight, does the captain get any notification if there's any flame somewhere on the airplane?
The only, well, not flame, he would get smoke detectors in the cargo compartment, and you can correct me if I'm wrong. That's the only area where there is a smoke alarm. Obviously, the lavatories now have smoke detectors, but now we're not allowed to smoke anywhere on the aircraft. But that was a big concern. When I was at Britannia, this was before that smoke rule came in. We were going to put smoke detectors on our aircraft. The Britannia's was a charter airline, part of the big Thompson group, which is a Canadian group, I think. But they typically took school kids on trips across Europe. And the big concern was that the kids would go into the lavatory and smoke, because it was allowed on the aircraft at that point. And if someone knocked on the door, they'd put it in the waste bin. So we were going to install smoke detectors in our aircraft anyway. So I had the opportunity, and I did smoke a little when I was back in the day. And so I volunteered myself to go and
Free cigarettes, right?
yeah, to fly on a 37. We put a actually we tried different smoke detectors, and the differences with the photoelectric and the ionization type. There's different types, and they have different characteristics as how much smoke they can actually generate, or how much is required to make it work. So
the ionization actually works off of ions coming off the flame itself. So
right.
If you have a smudge pot burning, the ionization won't trigger.
Right, you're right. There's space for different environments. So anyway, I went in there and I smoked, and we had a little light that came on. So they actually allowed me to smoke in the lav, which was still not allowed. And another interesting fact, the rule to have ashtrays on lavatory doors is still in place. You'll find on every aircraft there's an ashtray on the door, because they never took the rule away. Even though we're not allowed to smoke on planes, on the inside and the outside of a lavatory door, there has to be an ashtray. Isn't that crazy? Anyway, I think that's coming out on the new rule. I think that's one of the things that's been changed. All right, the seat cushion test. This is the burner that we make. It was developed by the FAA to be a consistent flame. Basically, we mix kerosene and air coming through this. We have a little atomizing nozzle that's in this area here, atomizes the fuel, and it just burns very, very good. And I showed you that picture already, but this is an actual, so before we start the video, so you can see the burner's gone. We burn it, light it up for 2 minutes. We measure the intensity of the flame. That's 2,000 degrees, 4 inches away from the flame. That's how we measure it. We have thermocouples that we check it before the test itself. This is the representative seat cushion I talked about. This one actually has 2 colors and the seat fabric, so we have to test both. It's a 4-inch thick and 2-inch on the back. All the samples are the same, no matter what the seat is. I mean, it'd be a business class seat with a big cushions or an economy class seat. This is the standard seat test that we do. It doesn't matter. We have a scale underneath here that measures the weight before the test, and we monitor that, and within the test parameters, you can only lose 10% of the weight of the cushion, which is nothing, because they don't weigh very much anyway. So it's a pretty strict test. We also measure the burn lengths on the fabrics or the seat cover at the end of the test. So it used to be they used to pushing the burner in front of the cushion, and it was very manual. We designed, or I wanted it to be automated, so someone in a different room, we're actually in a different room now, in a control room, and it's all automated. We have a motor that drives this into place. We can control the burner remotely as well, so it's all done remotely. This actually is at Recaro in Germany. I'm actually going there next week. We're doing some work on that scale. I've come up with a new solution for them. It's affected, the load cells are affected by the heat in the room and change just a minute amount, but we're going to put a cooling system onto the scale to try and keep the scale at the right temperature the whole time. So that's what I'm doing next week. Okay, let's start this video. I think you'll find this one good. So it traverses, this is our home position where we load the sample, we measure the initial weight, and we move it down into the burner. This is going to hurt. Yeah, and if there's any Velcro enclosures, they have to be on this side, because when you put the seat cushion together, there's going to be an opening somewhere to put the seat cover over the cushion, and we have to make sure that that enclosure is facing the burner, so that it makes it even worse than, you know, because the Velcro is never going to last that, but it will. Although they make no mix hook and loop now, which actually is much better than the old materials that.
Not much impingement on the back seat back there.
There's not a lot. Yeah, most of it's on the seat base. You're right, but this is the test as designed. I mean, we just follow the rules.
Yeah.
But you're right.
What's the time limit on that?
You don't normally drop a cigarette on your seat back here.
No, but if you dropped a cigarette, it would extinguish because we do a vertical burn test. They have to meet also an in-flight vertical burn. Sorry, who asked about the time?
Yeah, isn't it 2 minutes?
2 minutes. Yeah, it's impinging for 2 minutes. So it's a 2-minute warm-up, 2-minute test, and then we have another 5 minutes for it to extinguish or to burn out. So I'll just wait for it to move back, and then we'll. Interesting, you see that it's burning. There's not a lot of smoke that's coming off this at the moment. And this seat probably only weighed 10 kilos. The seat cushion itself, the two parts, weighed probably 10 kilos. What's that, 20 pounds? 20 pounds?
20 pounds, that seems like an awful lot.
Yeah, maybe. It's just that, but remember, these are not, this is a seat cushion designed for this test. It's,
You're talking about the whole seat assembly, the cushion?
just the cushions. We zero.
Seat and back?
Yeah, we zero it out before we put the cushion on, and then we weigh it when we put the seat cushion on. See, there's a lot more smoke coming off once it's charring, but you'd have thought that would still be burning, and that's amazing that it's just a few flames. Most times it'll continue on for that 5 minutes, and that's the end of the test at 5 minutes. We take that final weight and then evacuate the room. There's the thermocouples we use to test the weight, to test the temperature before. That just sits on top. I'm not going to go through yeah, it's almost done anyway. But it's quite surprising that all that heat and flame that was on, and it didn't do anything. That's new materials. That wouldn't have happened 30 years ago, trust me. That would have.
First officer said.
That's the first officer, yeah. Not the captain's seat, this first officer. Oh, I'm sorry, you're still. Oh boy. Okay, so that's that part. Now, fire containment, and I was a couple of weeks back. I was in Germany to test some galleys. It was for a retrofit program on Cathay Pacific on the 777s. They're having new galleys. The company I went to is the Safran company now, but it used to be Cell galleys, and they were the world leader in making large galleys for wide-body aircraft. Been there many times. It's a great little city. So anything on the aircraft where you store or put trash, be it in a lav or in a galley, trash containers, they have to meet a requirement for fire containment that if a fire started inside that trash container, that it would contain the fire. So with new galleys, they change the configuration of flappers on the top, flappers underneath, on the side, different volumes, just different ways that they come up with where they can stick this trash container in a galley. So we have to test for fire containment, and it has to be witnessed. And so I went over to Germany. They wanted 2 weeks to do 4 tests. The test typically takes between 15 minutes to 2 hours, but they said you're going to have to be here for 2 weeks to do 4 tests. And it actually took that time. By the time they set it all up and we checked it all out and they charged it. Anyway, you'll see more of that because I got some videos, and it's all monitored. We took videos to that, and they just build the part of the galley that has the containment. It's built to production standards. So you can see this is the trash area with a double bifold door, a countertop, and it's just the panels that surround that trash container. The galley is huge, but this was just the area where the fire containment was being tested. There's the opening on the top. It was a lift up. This was in the galley, so it didn't have to have an automatic. It was you lift it up, drop the trash in, and that's looking down on top. It was an all steel, aluminum deck with a stainless door. Most galleys have an insert, a metal insert that the trash falls in, so they can clean it out at the end or during the flight. But these can get lost, and so we have to do two tests. We do a test with the metal bin inside, and we also then do a test without that in case it's missing. If it's missing and it wasn't tested, then the aircraft can't. You have to totally. The aircraft won't be grounded, but you can't put any trash in that container during the flight because it's part of the MEL, right? So we always test without the container, which is a much more stringent test because the metal contains a lot of the heat, whereas without, you're just burning just inside the whole compartment, and you'll see that in a minute as well. But that's a typical trash container.
MEL being
minimum equipment list. Yeah. So what we do is we fill it 3/4 full with a charge of, it's a combination of paper towels, paper tissues, cups, crumpled cups, and still the rule is cigarette packets. But we have to, because it's in the rule, so we have to find cigarette smokers and we save the little packets. And we crumple them all up. There's a certain ratio that we have to put in the charge. That gets put inside the trash compartment here. And then we're all prepared. We've got the TC running, we've got video cameras going, and then some poor person's got to light it. And we have to make sure it's lit. So this is the... And we have to make sure that at least 50% of the surface is burning before we start the test.
Okay.
Yeah, that was good. Close the door. We obviously couldn't light it from the top because you'd get burned. So it was good we could light it from the door. Now we'd run out of the room. A couple of things. The doors, we shim all the doors with an opening to simulate misalignment of the door latch. Because obviously the fire will be fed by any oxygen that's getting into the compartment. If it's totally sealed, it'll just go out. But in service, the doors are going to the hinges are going to get loose, or the latches, and so we simulate by putting shims on all of the opening surfaces, the doors, that flapper on the top, we put a shim in, so there is some airflow possible through the unit.
Worst case scenario.
We have to look at that. Yeah. So this was, is that still video? Oh yeah. So this was the first test we did. You can see there's a little bit of smoke coming off. And that's coming at that flap on the top, and that's where the little gap is. This test lasted, I think, maybe 15 minutes. What we look for on the graph, we look for a peak on the thermocouple to make sure it is continuing to burn. I think it's 500 degrees it has to meet, and then once the fire's going out, the temperature will start to drop, and once it reaches 150, then the test is done. This one, like I said, took about 15 minutes.
Hey Martin?
Yes.
Most of the 737s I was in, they always had plastic totes. Would they be inside of a metal?
No, I mean we test it with plastic, and as long it doesn't matter. It doesn't have to be metal. I mean it can be plastic. Okay. Yeah, but we test it with that.
Yeah, so that where you would put this plastic tote for the garbage, that would be sort of a metallized.
It doesn't have to be. It can be plastic. I've seen plastic waste containers go in there. Yeah. And that was what it came out at the end. You can just see it didn't burn the whole charge up. It extinguished. And I think some of it was the heat that was absorbed by the can, and it was a smaller volume. So after that, now we really got a time. We fill that. This is simulating without the containment, the bin. Sorry. So we just fill that hole up. We can see the paper cups. You may see an odd cigarette packet, paper. There's crumpled paper towels and tissues and all sorts of good things in there. But we have to fill it up 3/4 of the whole volume, whereas on the bin it's 3/4 of the bin. So this is a much more stringent test that we have to do here. Same sort of idea. This time we couldn't open the door because it would all fall out. So this time we had to drop it in from the top and then watch it.
Okay.
Mass exodus for the door there. So you can see already there's a lot more smoke that's being generated from this. And so it actually got to the point in this test, this took almost 2 hours to self-extinguish. It didn't burn through, as I'll show you at the end. I can show you pictures at the end. But the amount of smoke in that room, we couldn't even see. There's a clock inside that we watched to take pictures every 2 minutes. Couldn't see the clock. We had to rely on our watches. And even the control room that we were in, that filled up. So we sat outside. It was... But it passed. I mean, that was the end of it.
What was the material they used to build the cabin in there?
That's just fiberglass panels. They're just the typical phenolic panels, honeycomb.
But no real damage, just sat there and smoldered.
It just sat there, and it popped. I mean, actually, I don't know if you'll be able to hear it. I'll let it run for a minute or so. But the honeycomb, it was the heat inside. Actually delaminated that was a pop there, delaminated the panel. The panel the skin pulled away from the honeycomb just because of the heat that's been generated. But it didn't penetrate. That was the whole idea. It's fire containment we're doing. I mean, there can be damage for sure, but it's just how that you don't have fire coming out. So the idea on this is it's a galley, so it's accessible. So hopefully an attendant or someone would notice there's some smoke and they'd fight the fire before it got to this point. But the idea is you have to make sure it contains it. Well, what was happening also is we would start to drop, the temperature would drop, and then an ember would drop onto the next layer of paper towels and would fire up again. And we'd have this fluctuating temperature. So that's all. You can see it's all layered, the smoke's all layered out, but it gets to a point where we can't see this clock. Anyway, I don't know how this is too long a video. Yeah, let's move on. So that was at the end of the test before we opened the door. You can see the flame.
How long you said you had it?
This was almost 2 hours. This one went. Yeah, it was a long time. It was because of the volume. There was still obviously oxygen inside that cabinet, and maybe because of the gaps. You can see there's a shim there. Like you can see the shims we put in to keep the door just a little bit open. But you can see where the heat has come through the panel itself. And that was when we opened the door. You can see it pretty much burnt the whole of that charge of material.
That's after a 2 hour.
That's after 2 hours, yeah. That's it in the bottom. There's the bifold doors. And you can see the delamming that occurred. But it contained the fire. And that was after we'd moved all the material out. And I think that was the end of it. So that was a couple of weeks back. I did that. So
Question.
Yes.
The last picture you showed us before you got into the videos, and you were saying something about foam that was like an inch thick, or you said it was fire resistant. Is that something that might be applicable for general aviation use for a firewall?
the one that burnt?
No. It was you had a horizontal or vertical.
Vertical test. I wouldn't put it on a jet aircraft, no. Particularly a firewall. Firewalls actually have to be fire resistant, and they have to meet a burn through test. So typically there has to be a stainless or at least a thick aluminum for a firewall.
Or that insulation could be put in front of that, though, perhaps.
You could put the insulation, yeah. You could put it in front if you wanted to stop any noise coming through. Yeah, that's totally fine.
And heat, for that matter.
And heat, yeah, for sure. But I mean, I wouldn't, even for GA aircraft, I'd probably want to make sure that material isn't going to burn. At least a Bunsen burner test. You don't have to do a radiant panel test for a GA aircraft. That doesn't apply. But I'd certainly make sure it doesn't burn. Do a quick Bunsen burner test, or have one done. A little lighter, you can test, with a lighter and see if it's going to burn or not. A little lighter will give you almost the same heat intensity. But anyway, hopefully that gave you a bit of an insight into flammability on the aircraft. Yes.
Can I take a minute to share a little story that might kind of bring this down to the GA level?
Yeah, go ahead.
Well, several years ago, I went to Wichita and Bombardier Learjet's safety stand-down program, and they have a whole sequence of seminars that you could go through. And one that I selected to go through was the fire in the aircraft scenario. And everybody that was in attendance there were professional pilots. They were Learjet pilots, Gulfstream pilots, airline pilots. So everybody was a professional, was trained, had previously through the airline training gone through the sort of in-flight fire emergency training that you would expect. And the scenario that was involved, there were two separate simulators that they had there that were aircraft cockpits, bizjet cockpits. And we were put together in groups, and one person was assigned to be the captain, one person was assigned to be the first officer, and the rest of the people, remember, all professional pilots, were assigned to be passengers. The captain gave the orders to the first officer briefed the passengers, remember they're all professional pilots, on what to do in the event of this in-flight, in the event of this in-flight fire emergency. And then they had a smoke generator that produces smoke so thick that airline guys have probably all gone through this, that is so thick you literally can't see your hand in front of your nose. And here's the jaw-dropping experience that I had, and I've been flying, if I make it to September, for 50 years. This was just shocking to me as to how quickly the organization and the skill sets of all of these professional pilots completely fell apart when there was a fire. It just completely fell apart, and things didn't get done, and people would have died. The airplane probably would have crashed. Now, maybe when we got through that training, we're a little better prepared and might try to avoid it. The moral of the story is, everybody probably agrees, fires in airplanes are bad. But really, if you get a fire in an airplane, you got to get it on the ground right now. Like, that's what you're trying to prevent, is deaths and injuries, loss of the aircraft associated with fire. While in a G airplane, we don't have that luxury of all this careful testing. So get a fire, get it on the ground.
So there is GA Part 23 does have flammability, and so the manufacturers do have to meet Bunsen burner tests. That's all though. No heat and smoke, no toxicity, no radiant panel, just the basic Bunsen burner test when they certify the aircraft initially. When you do interior retrofits, I know you can buy kits for new trim, and they say it comes with an STC. So the STC, the manufacturer has to do testing to meet that requirement still. So make sure if you do buy parts on an aircraft, it's got an STC part of it, because that means it's been certified by the FAA to meet the requirements.
So first job, fly the airplane.
Yeah, that's always the case. But yeah, get it on the ground. Get it on the ground as soon as you can. That's I agree. All right. Any other questions? Hopefully that gave you an insight into what I do for a living and we build all this equipment down in Bellingham. And like I say, when I've got some of the equipment running, I'll get Bryant to send out an invite. You're more than welcome to come and watch one of these machines in operation. The oil burn test is the fun one to see, because that's a huge flame and it's just fun to watch. But the other tests, you're more than welcome to come and see what we do anytime. There's an open invitation for anyone who wants to come and take a look. Alan's been to my facility before. I don't think anyone else has been. But anyway, anyone's welcome to come and take a look. There's only 7 of us, but like I say, we cover the world with our equipment.
Pretty cool.
Yeah, that's what we do. Anyway,
Thanks.
you're welcome.
So So did you get in trouble with your mom for trying to burn things?
I was never a pyro when I was growing up. I don't believe anyway. This, like you said, I was just asked one day, "Hey, do you want to become a flam DER?" And I had to research into what it was. But it's been a great opportunity for me. I've learned a lot, and I've visited a lot. You know, I've covered the world because of flammability. I mean, it's fun. It's been a good thing for me. So it keeps me too busy. The other projects I've got are